Last time we started to speak about the standing wave along the transmission line. The standing wave is a result from the interference between two traveling waves. So we have two traveling waves. One wave going from the generator to the load. This is a forward wave or incident wave. Another wave going backward from the load to the generator, which we call reflected signal. And the cause for the reflection is the change in the impedance between Z0 and ZL. Yani we have different load impedance than the characteristic impedance of the line. So while the wave is moving, if this transmission line is infinitely long, do you think we'll have any reflection? If this line goes to infinity, would we have reflection?
No.
No, there's nothing will come back. It's the same impedance to infinity, so there's no reflection. The reason we have reflection because of the load is different than the impedance of the line. So when you see something different, there's some result which is the reflected wave from the load to the generator. And the evidence for this, this makes sense because we have found from the equation, this equation shows the reflection coefficient at the load as the ratio between the reflected signal, the backward signal, over the forward signal. Look at this signal, look at this equation. This equation gives you the ratio between the reflected signal over the incident signal at the load, exactly at the load. If you look at this equation, if ZL happens to be the same as Z0, you will have no reflection. All the energy traveling will be absorbed by the load if ZL equal to Z0. And we have made this equation simple by dividing the numerator and denominator by ZL by Z0. Now we have this new parameter which we call what is the name of this ratio? Normalized impedance. Normalized impedance means the impedance over Z0, the load impedance over Z0. So we call it ZL small z, small letter z, okay? So big letter means the load itself. ZL over Z0, small zl, which is the normalized impedance. From this equation, we can see that the load reflection coefficient is based only on one parameter, which is small zl. Okay? So one parameter only controls the load reflection coefficient. We need now to understand how the standing wave are behaving, or the relation between the standing wave and the two waves traveling, the forward wave and the traveling wave. We have done simple derivation last time, and we have reached to a very powerful equation, which is the magnitude of V of D. V of D is the magnitude of the voltage in complex domain, in phasor domain, along the transmission line. If you remember last time, we said that we have two distance coordinates. We have Z equal to 0 at the load, and then Z any negative value until the generator Z equal to negative L. The reason we choose this configuration of the coordinates to make the math easy. Okay? So Z is always negative, from 0 to negative L. At any point, Z is negative. We have another distance coordinates, which is D. D started at 0, at D equal to 0 at the load, and D is always positive. At the generator, D equal to L. So at any point, Z equal to negative D. At any point, Z equal to negative D. We like to work with D because D is always positive. We like to work with D because D is always positive. Initially, we have the equation of V and I along the transmission line. يعني في الأول we have V and I was based on Z. And Z is always negative based on this choice. So it's our choice, by the way. يعني I can't choose Z to be positive or negative, doesn't matter. But I choose to be negative to make the math easier. And I will now transfer from Z to D. I will use D. D started at D equal to 0, and then it will be positive value. Last time we have reached to these two equations, which are very important to understand the standing wave pattern or the standing wave behavior. The definition of gamma is the ratio between the reflected over the incident wave at the load. So if you are here, you have two components, reflected wave and traveling wave. There is no e to the power because Z equal to 0 here. So e to the power gamma or beta is 0 because Z equal to 0. So it will be 1. E to the power 0 is 1. So there is no exponential here. It is only a ratio. This is the reflection coefficient at the load. This is the definition of V and I at any point D. At any point D as a magnitude. What do you notice with this equation? You have positive here, negative here. Everything else is the same. And the magnitude is, or this parameter is reduced by 1 over z0 because this is the current, V over Z. What do you notice here? You look at these two equations, you have positive, negative. What is the result of this? Of these two different opposite signs? يعني, what would you expect?
You think at the voltage when it's peak, current will be smaller.
Yes, from these two opposite sides, if the voltage is maximum, current will be minimum. Why? Why, Reda? Because of the cosine here. Look at the cosine. What is the best value of cosine to make this guy maximum? What is good value of cosine? 1, 0, negative 1. 1, right? So 1 will make this guy maximum. And the cosine will be 1 if the argument equal to 0 to pi, 2n pi, right? 0 to pi, 4 pi. If under this condition, when the cosine is 1, this guy will be maximum. Agree? This guy will be maximum. What about the current? Magnitude of the current along the transmission line. If this guy is 1 here, the same. So this is 1 and this is also 1. The current will be minimum or maximum? Minimum. Because I have negative here. Negative, the maximum of cosine is 1. This will make the current minimum. So it's clear that the current and the voltage are behaving oppositely. If the voltage is maximum, the current will be minimum and vice versa because of this change in sign. Okay? And what about the minimum? How can I make the voltage minimum? This guy, how can I make it minimum?
Negative 1.
By make the cosine 0, 1, or negative 1?
Negative.
0, 1, negative 1. 0, sorry, negative 1. If the cosine is negative 1, if the cosine is negative 1, this is going to be minimum, clear, because you have plus here. So this will be negative, will make the whole thing. And if this is negative 1, this means the argument, this part will be equal to, the line inside will be equal to by 3 by 2n plus 1 by, right? By 3 by 5 by. If the voltage is minimum under this condition, under this very condition, when the cosine is negative 1, so the cosine here also will be negative 1. Under this condition, when the cosine is negative 1, this equation will maximum or minimum? Maximum, because I have negative here. So is this clear? If the one of them is maximum, the other will be minimum. Okay? What else you notice? So the two guys are behaving oppositely. So looking at the behavior, this is the two equations. Remember these two equations I have just written? Magnitude of V of D, magnitude of I of D. When you sketch them, it will be sinusoidal waveform. Look at the behavior. When one of them is, this is the voltage, magnitude V of D, this is the current. When the voltage is minimum, current is maximum, and vice versa. Okay? What else you notice? Look at this graph. What else you notice? In this figure, which is the magnitude of the complex voltage over D at any distance along the line, and this magnitude of I of D. This is D, not Z. This is D. What do you notice, Shabbat? Yani if you go from here, from this point, from maximum to maximum, is it lambda or lambda over 2?
Lambda over 2.
The repetition is lambda over 2, not lambda.
Yes.
Why? Why? Why the repetition is lambda over 2? It's clear that if you go from maximum to maximum, usually it is lambda. Like the two traveling wave. Remember the two traveling wave? They change every one complete cycle every lambda. The forward and the reverse wave complete one cycle, each lambda. Here, for the interference, the two guys together, this plus this give you repetition at lambda over 2. Not lambda. What's the reason for this? There are two reasons. There's mathematical reason and the intuitional reason. Okay? And there's logical reason or physical reason and the mathematical reason. Look at the equation. Look at these two equations. Is there something, sorry, Abdullah, is there something in these two equations that indicate that the repetition period will be lambda over 2, not lambda? Yeah, Abdullah, صح? Ryan, yes,
The square root. Is it?
not directly. Yeah, it is part of the equation, but this not directly is the reason we have a repetition at lambda over 2.
2 beta.
2 beta, look at 2 beta. 2 beta will make the repetition lambda over 2. If you have cosine x versus x, this will complete one cycle with x equal to, make it sine. If this is sine x, this will be 2 pi, right? X will give you 2 pi. If the sine x becomes sine 2x, make it sine 2x versus x. It will complete one cycle when x equal to pi, right? Because it's 2, which appears here, which will make the repetition lambda over 2, like this behavior. And also, if you remember in chapter 1, we have defined the traveling wave to be cosine beta x minus omega t. Remember this equation?
Yes.
Beta x was beta, 1 beta only, not 2 beta. 2 beta will make the repetition lambda over 2. This is the mathematical reason. In mathematics. What about the physical reason? Yes, yeah.
Well, we can make the incident wave as a car and the reflected wave as a car. If they are moving towards each other, the relative speed for one car to the other is double the speed of one of these cars.
Is seeing when 2 cars are moving opposite to each other, and then you add them together as a 2 speed?
No, if you compute the relative speed of the one of the cars to the other, will be double the speed.
He's saying if you have 2 cars moving with the same speed, one car will look at the other car as twice the speed. Make sense? Huh? Make sense? Maybe makes sense. It's a good attempt. If you write standing wave here in Google, there is nice animation that I showed you many times. Where is this animation? Image. Look at this animation. This animation explains why the red signal is a standing wave. Okay, the blue signal is the green one is a traveling wave. The generator is here and the load at the other side. Right? Okay, this bit. So the green one is the traveling wave, the incident wave, the blue is the reflected wave. The green one, sorry, the red one is the summation. Green plus blue give you the red one, which is the standing wave. Guess what is the load in this case? How much is the load? Is it 0, short circuit, open circuit?
Should be open circuit or
Huh?
short or open.
It is short or open. It is not 0. Sorry, it is not Z0. Yani the load, we have 3 main cases. Either the load equal to the characteristic impedance, which will have perfect matching, which will mean perfect matching. So the blue signal should disappear if the load equal to Z0, which is not the case. What we have here is full reflection. Everything coming through will go back. All the green signal is going backward. There's no energy absorbed by the load. There's no energy reaching the load. Everything is going back. They have the same magnitude. So the load here, look at the standing wave, it has 0 voltage. So the load is short circuit because the standing wave gives you 0. If this open circuit, you will find this point will be at some magnitude here. It will go up and down. For short circuit load, the voltage is 0, right? For open circuit load, the current is 0, the voltage is not 0. For short circuit load, voltage is 0, current is not 0. So this short circuit load, which reflects everything back. So on the, if you look at the red signal, we have points that are called anti-node, which is the 0 point. The 0 point is always the same place. Yeah, the red signal has 0 point at the same place, and has maximum and the minimum at the same place. The formation of the nodes and anti-node will take 1 lambda from the traveling wave. And for each 1 lambda of the traveling wave, you will have one of the anode, then antinode. So it will take half the space, the wavelength of one of the traveling wave. Okay? Think about it with some imagination. So the repetition period is lambda over 2, and we have seen there is some mathematical reason and physical reason, as we have seen from the propagation. We need now to find out the value of the maximum of the voltage. We are looking at these 2 equations. What is the maximum V of D. What is the maximum magnitude of V of D? When the cosine equal to,
1.
when this cosine is 1, so this equal to 1. This equation will be, when this guy is 1, what is the new equation? 1 plus gamma squared plus 2 gamma, which will be like magnitude V0 positive times 1 plus gamma squared. Does this make sense? Right? Am I right?
Yes.
So based on gamma, if you have magnitude of gamma and V0, you can find V maximum. The book already assumed some value for V0 and gamma, magnitude of gamma, so you can find the maximum voltage. What about the minimum voltage? Yeah, this is the maximum voltage. What about the minimum, if I need to find the minimum? Minimum means the whole guy equal to -1. Right? The whole guy is -1. So what's going to change here?
The sign.
1 plus x squared minus 2x. Means you have 1 minus x, right?
So
Yes.
doesn't the
1
square root
minus x squared.
doesn't the square root take the square? We have square root here. in the-
Yes, we'll remove this guy. Okay? يعني max and minimum could have because we have 1 over 2 here. Okay, شباب? So the maximum voltage which will happen when this is equal to 1, it will be V0 positive 1 plus gamma, 1 plus magnitude gamma. Change it to minus, this will be the minimum voltage. This is the minimum voltage. Very easy. يعني make this guy 1 or -1. This will give you the maximum and the minimum voltage. What about the, I need to find the distance from the load when the voltage will be maximum. I need to find E that will make this guy maximum. At what distance we agree that D equal to 0 at the load. Then D increases. At what point the voltage will be maximum? Assuming the voltage is something like this. So at certain point D, at certain distance from the load, the voltage will be maximum or minimum. What is the distance at the first time when the voltage will be maximum? Just take this guy. The argument will be equal to, what's the condition for the cosine? Cosine must be 1. So cosine this guy will be equal to n bar. Agree? 2 n bar in 0, 1, 2. And then solve for D. This will give you D at the maximum voltage. What about if I need to find D that will make V minimum? Take this guy and make it 2n plus 1 by 3 by 4, as you know from math, from all courses. So we can now easily, and from this two equations, we can find out the maximum. This is the maximum voltage, as we said. This is the maximum voltage. V0 positive plus 1 plus gamma. This is a general equation for any transmission line, for lossless transmission line. Based on V0 and gamma, you can find the value of and this is a minimum voltage, 1 minus, only change is minus. Okay? The D maximum, as we explained, this is a phasor diagram or magnitude of V of D. Look at this equation, magnitude of V of D. Assuming the load ZL equal to Z0. Assuming ZL equal to Z0, which is a perfect matching, no reflection. Everything will be absorbed, all the energy traveling will be absorbed by the load. Nothing will going backward. In this case, Abdulaziz, when Z equal to Z0, what does this mean, Abdulaziz?
This means there is no
No reflection, okay? And the gamma will be, what is gamma now? Gamma is the load reflection coefficient.
it will be
Do you remember the equation, Abdulaziz?
yes.
What's the equation for gamma? Gamma equal to what, Abdulaziz? The load reflection coefficient.
ZL minus 1, ZL plus 1.
ZL, we can take the big Z, ZL minus Z0 over ZL plus Z0. Agree يا شباب? If you take the ratio over Z0, it will be small z, which is the normalized impedance. So assuming the two guys are equal, the gamma will be what, يا عبد العزيز? Gamma will be
0.
0. This means no reflection. If gamma equal to 0, what is magnitude of V of D? What is this guy? No. If gamma equal to 0. It will be this one, which is constant. Okay, so this is the phasor complex voltage, which is the envelope of the time domain. Yeah, looking at this signal, this is the magnitude of V of D, the magnitude of the complex voltage on the transmission line at any point D. At any point D, you have the same magnitude of voltage. What does this mean? In time domain, this is the phasor domain, the complex domain. Magnitude of the complex V. What about the time domain? How does the signal look like in time domain? Again, for the perfect matching, no reflection. The best case, all the power is being absorbed by the load, no reflection. Z equal to Z0. Magnitude of V at any point is the same. This means what? In time domain, if I need to sketch V of D versus time, how it will look like?
Sinusoidal.
Sinusoidal waveform has the same magnitude, will be something like this. And moving with time, with the same magnitude. It will only move with time, doesn't go up or down. This is a traveling wave, which is the same as, which is the total wave. There's no reflection. Okay? What about if we go, so what we understand now is that the phasor voltage is the envelope of the time domain. And if you look at the time domain, I need you to understand what I'm saying here. The time domain, this is magnitude of V complex. If we go for V of D as a time domain, V of D and T versus T at any point, it will be something like this. And moving with the same magnitude. So the envelope of the wave is the magnitude we see here. Yeah, this curve is the envelope. Do you know what's the meaning of envelope?
Yes.
370. So the envelope of the wave is the same as the curve you see here. Okay? What about if the there's a nice video shared by someone called Ahmed Al-Hussein. Where are the other guys? I have shared some videos here for you to watch. What is the copy? Solution. These are the videos I have received from you. So I have collected them in some folder here. If you look at this video by Mr. Ahmed Al-Hussein, I think it's a nice video to see the time domain and the phasor domain of the wave. So assuming I have a transmission line with these characteristics, the characteristic is that the load impedance, and assuming the load impedance is the same as characteristic impedance, and the load, we will have two cases, either the load equal the characteristic impedance, or the load is different than the characteristic impedance. And we have another case when the load is short circuit and open circuit case. So we have now two cases. This is animation. If you go to the web link I always share, you will find this window. So here you can define the characteristic impedance of the load and the load impedance. So in this case, in this window, I will have the load equal to Z0. This guy equal to this guy. This means no reflection. Okay, so in this case, the load equal to the transmission line impedance, no reflection. In the other case, I will make the load. Here, when there is no reflection, look at the wave propagation. This two red line is just envelope. It has nothing to do. We look only on the blue signal. This is the case when you have no reflection. You will see the wave is traveling, no attenuation, no variation along the y-axis. Perfect sine wave, cosine wave, traveling, and no reflection is taking place. This is the total wave, the summation of the reflected plus incident. We have no reflection. Okay, the red line is only the envelope, the cover of the wave. Let's look at the other case, when the load is 100 ohm and the impedance was around 50 ohm. So the load here is 100 minus 50 over 100 plus 50. What is gamma? If this guy is 100, this guy is 50, what is gamma?
Another 3.
0.3?
1 over 3.
1 over 3. So assuming this guy is 100 and this guy is 50. So it's 1 over 3, right? 1 over 3, this means 1/3 of the wave will be reflected back. One third, so the gamma here at the load is 1 over 3. And the phase, what is the phase? Gamma usually is complex, the phase is 0, no phase. Because the load is real. Z0 is always real if the line is lossless. If the load, usually it is complex number. Usually it's complex. Here, in this case, it's real number, so gamma has no phase. This means 1/3 of the wave will be going backward. Yes?
Because the real number of gamma represents how much of magnitude the reflected wave will be.
Not magnitude. This is the ratio between
Yes.
the reflected signal
Yes.
to the incident signal.
So if it has a complex value, what does that mean?
This means there is a phase difference between the two signals, V0 positive and V0 negative. Because this is the ratio between the reflected wave, V0 positive over V0 positive. This is the ratio at the load location only. So if there is a phase here, this means the two guys are having phase difference. They're not starting at the same point. You know what is phase difference?
Yeah, but that will not affect the standing wave.
It will affect the standing wave, of course. Standing wave is controlled by the magnitude and the phase. The phase is related to the speed of the wave, or how the wave is propagating along both time and the space. Okay, so the phase is a big part of the magnitude. Now, assuming under this condition, when ZL is 100 and Z0 is 50, gamma is 1 over 3. Look at this propagation. Now look at this. Here, no reflection. Here we have some reflection. So look at the propagation of this guy and this guy. What do you understand from this? No reflection. Here we have 1 over 3 reflection. What do you conclude? Who wants to speak? Can you say something? Okay, go ahead. The one behind.
The one of 1/3 reflection coefficient, that stable like.
Oh yeah, we have some kind of variation along why I am. Look at that. What's your name? Abdullah. Look. Seems the first of the class is Abdullah. So if I forget your name, I will say Abdullah. Look here at the propagation. The y magnitude, the magnitude is like stable. Here, the magnitude go up and down. It's not attenuation. This is not attenuation. This is due to the reflection. If you have attenuation, the wave will decay like underdamped in RLC circuit. This is not attenuation. Here we have the effect of the reflection. Okay, we have some reflection. Some reflection means we still have propagation. Look, the signal is propagating, but it is not like the case when you have no reflection. And here we do have propagation because the signal is not fully reflected. And some part is reflected and some part is incident. The total reflection plus incident wave is this blue thing. And the red one is just the envelope. And it shows you the envelope. The red one, look at this red one or pink one. This is a complex magnitude, which is magnitude of V of D, which we have just seen. If you look here, if we plot the magnitude here, as we have just when Rida helped me. It was Rida or Abdul Aziz helped me. This is the magnitude of V of D, the magnitude of the complex voltage. It's constant, because gamma is 0. Here's the magnitude of this guy, is this red line. This red line is the magnitude of the complex V of D. It gives you indications that the signal is experiencing some reflection. Okay? So we have seen no reflection and some reflection. What about if we have full reflection? So everything is going backward, which is the case when we have short circuit load or open circuit load. How does this look like? Yeah, let's look now at the extreme case, the worst case, when everything is going backward to the load. What would be the behavior of the time domain? This is a case when we have short circuit load. Load is short circuit. Look at the wave, the blue one. Before it was propagating, only have some reflection. But here everything is going backward. So it is fully standing wave. Doesn't go anywhere. And you can say here partial standing wave, because still moving. But this guy is fully standing wave. It go up only up and down as a magnitude. It doesn't go anywhere. The zero location is fixed. The maximum location is fixed. What is the voltage here? Zero. Short circuit. Voltage is zero. Okay, Shabab? This is the case of short circuit load. The signal is not moving anywhere. What about if I have open circuit? What will be the propagation look like? What do you expect, Shabab, if we have open circuit? This is the open circuit case. Okay? Look, the signal now having some value here, because open circuit, the voltage is not zero. And it is moving up and down. It doesn't go anywhere. It doesn't go anywhere. Standing, fully standing. You can say this is partially standing, because some is already traveling, but with some variation. But here is fully standing. Okay, Omar? Lam. So please, this was assignment of the bonus. Did you see this? The bonus, the quiz 1 makeup, Tuesday 5:15. It will be in this building somewhere. I need to find the room. So this is the envelope when the load, the magnitude of V of t, when the load is Z0, when the load is short circuit, when the load is open circuit. Look at the difference between short and open. This envelope of the time domain, yeah, the time domain is moving up and down under this envelope. When you have short circuit load, ZL is 0, gamma is -1, you have 0 voltage here. Here, open circuit, you have some voltage here, which is twice magnitude of V0. So this is a complex, the magnitude of the complex V of D, which is the envelope of the time domain function, the time domain voltage. Okay, sure? I hope you are following with me. I'm not losing you. There are some examples in the book. We have a tutorial on Saturday at 1. Okay? Who is going to come? It is very useful. Please come to this tutorial. You will be taught with a PhD student here. It will be in Blackboard. Are you familiar with using Blackboard for online classes?
Yes.
You know how to use it?
Yes.
How do you use it?
خلع
Collaborator, I guess.
Yes.
There's three points there. You click 3 points, join. I created section. I created like appointment, and once you click collaborator, it will show event time. Click the event, it will take you to the session on Saturday at 1 p.m. This is the condition. If you remember, this is the condition for the maximum voltage, right? The argument of the cosine is 2 in the bar, 0 to pi. If I take D out, this will be D of the maximum voltage. So D of the maximum voltage is the same equation. Will be this guy. Okay? Just take D out of this equation. It will give you this guy. So look at this equation. I have two conditions here. When theta R, what is theta R here, Ashib? What is theta R?
Reference.
Theta R is gamma is normally magnitude and some phase. AJ theta R. Okay? Theta R is the phase of gamma. Gamma is complex, magnitude and phase. Theta R is the phase. Okay? So why I have two conditions here? Why I created two conditions? This is the location when the voltage is maximum. Why I have these two conditions? Look at them. Yes.
For open and short circuit.
No.
Conductive or
D will never be negative value. Remember, D is 0 at the load, then positive along the transmission line. D negative is outside the load, outside the circuit. So to avoid having negative D, if theta R less than 0, and n equal to 0, assuming n is 0, and the theta R less than 0, D will be negative, which doesn't make any sense. You are out of the circuit. So I have created this condition. If theta R less than 0, I exclude 0 here. 0 in the other case when theta R bigger than 0. To assure that D maximum is always positive. Must be positive, it will never be negative. Okay, Shabab? Also, what about D minimum? So D maximum now is known from this equation. D maximum is here, assuming it's here. D minimum is D maximum plus lambda over 4. This lambda over 4. From here to here, lambda over 4. So if you know D maximum, you can find D minimum. Okay? D minimum is the maximum, which we have just found, plus A, plus lambda over 4. Just add lambda over 4 to D maximum, which you can find from this equation. Or you can find the minimum from the condition of the minimum. You make the argument to n plus 1 bar, the argument of the cosine, if you like. Yeah. This conclude, there are some examples that you can look at. One last thing. We will define something called standing wave. Standing wave is the ratio of the maximum voltage, the maximum complex value, over the minimum value. The ratio is 1 plus gamma over 1 minus gamma. Okay? What does this mean? What is the ratio means here? This is called standing wave ratio. Its indication, standing wave ratio, the ratio between the maximum to the minimum voltage, is indication how much reflection you have. Gamma, magnitude of gamma. What is the limits of this magnitude of gamma? What's the minimum magnitude of gamma? Minimum? Maximum? Minimum is 0, 0 to 1. It will never go outside this region. When magnitude of gamma will be 0 when? What's your name? Muhammad, magnitude of gamma will be 0 when, ya Muhammad? لا. When is this guy equal to this guy? When is this z equal to z0? Gamma will be 0. Right? Which is no reflection. It will be 1 when ZL is 0 or infinity, open or short. So this is the extreme point, the minimum and maximum. It will never go beyond this. Okay? It will never be bigger than 1. Do you know why it shouldn't be bigger than 1? لا the reflection coefficient. It will never be 1.
Reflection will be more than the original signal.
You are sending some waves, then you are receiving reflection more than what you are saying. Doesn't make sense. So it will never exceed 1. So based on this fact, that magnitude of gamma from 0 to 1, S will have limits from what to what? When gamma is 0, the best case, no reflection, S will be 1. And then when gamma is 1, magnitude of gamma is 1. The worst case, what is S? Infinity. So the ratio, the limits of S from 1 to infinity, it will never go outside this range. The best is to have S equal to 1, which means no reflection. The worst is to have S as bigger as possible. The bigger S, the worse the case. The more reflection you are having. So it's another indication. And instead of speaking about gamma, we usually speak about S. When you go buy some device, they will tell you S of this device equal to 1. So S is indication how much reflection you have. The more S, the more reflection. This means you are approaching 1. Okay? Commercially and practically, it's better to work with S, to express the performance of your device based on S, not gamma. Okay, Shabab? This is the standing wave ratio. It's called the standing wave ratio. The ratio between V maximum and V minimum. Which is what? What is the ratio here? V maximum here equal to 1.3. V minimum 0.7. So it's 1.3 over 0.7. This will give you S. Again, it has limits from 1 to infinity. It will never go outside these limits. This simple example you can look at. Another simple example. We will have tutorial on Saturday, so you should. I'm not going to solve problems in class unless something very critical. The problem will be solved on Saturday. Does this make sense? Yes. So we'll focus more on the concept. Now we move to the new part, which is wave impedance of transmission line. What's the meaning of wave impedance? Look at this is a transmission line. Okay? Load, generator, D equal to 0, D equal to 0 here, D is increasing at the generator, D equal to L. If I cut the transmission line here, if I cut here, like Thevenin, you know Thevenin equivalent? Yes. If I cut here and look at this side, so I will replace the whole thing by one impedance called ZD. ZD is the impedance replacing all this part at any distance D. What is ZD? ZD is the wave impedance. ZD is the wave impedance. Okay, Shabab? So I need to find the impedance at any point along this line. Is it the same impedance? And if I cut here, 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 is it the same?
No.
It is not the same. Because if you remember the voltage along the line is based on D. This is what distinguishes what you are doing from circuit theory. It's not circuit theory. This is not short circuit. Yes, Abdullah.
يس دكتور الان انت لما قصيت السيركت الترانسميشن لاين هل رجعت مع بعض يطلع لنا زد دي ما فهمت كيف وصلنا للسيركت اللي تحت.
يعني assuming I'm here, so I remove the whole thing and replace it by impedance ZD. So this guy, whatever here is still there.
حلو
I
يعني
replace the whole thing by ZD like similar equivalent.
يعني انت ما جبت
زي input impedance, this is input impedance of this part.
يعني انت ما جبت امبيدنس من برا، لا هذه الامبيدنس حقت الترانسميشن لاين بس.
Exactly, at this location.
جميل.
Okay? What is this? What is the definition of this impedance? What is the definition of this impedance, Shabab? So again, at B, at point B, I will move the whole thingy and replace it by ZD. What is ZD? What is ZD here at this location?
ZL plus the
V of D over I of D.
IFD.
Simple, V over R at this location. We have V and we have R, right?
Yes.
Which positive, negative, and that's it. This is the whole impedance. V of D over I of D. But it will be a big equation. We need to make it simpler that we can handle. So this is a class how to replace the whole thing by some impedance. If we are at the generator, if you stand up here, if you remove the whole circuit and remove the whole thing and replace it by some impedance, the impedance will call Z input, the input impedance. So the input impedance is the equivalent impedance at the generator side. Now if you cut the circuit here, the whole thingy will be Z input. So it will be easy to handle now. Much easy to handle. Now this circuit thing, 201. No transmission line here. So what is the voltage here, V input? Yeah, looking at this circuit, if I need to find the voltage here, at this point, how can I find it? Like here, forget what this here. At this point, what is the voltage? I need to use this big equation, right? What about if I replace the whole thing by Z input? What is the voltage now here? Voltage divided. VG over ZG plus Z input times Z input. Which is divided. No transmission line here. 201. Okay, Shabab? So the question is how can I find Z input or ZD at any point? Very simple. This is the idea. And the math is very easy. Inshallah will be very easy. I define the voltage here as VR, V input and I input, V input, I input. And we have here VL, IL. VR, I input, VL, IL. Stop the video.